Hello, everyone, and welcome to the Zero Emission Buildings Academy. I'm Quentin de Hulst, the Director of Green and Healthy Buildings at the European Copper Institute. And we are launching this series of webinars in partnership with the Building Performance Institute Europe and the European Construction Technology Platform. Our aim is to promote the transition to a zero-emission building stock. It's a climate policy objective in Europe that also brings multiple benefits. And we know that the implementation of the necessary renovation wave requires actions at all levels of the political governance and of the value chain. Just today, 1 hour ago, the European Parliament adopted its position on the revision of the Energy Performance of Buildings Directive that will now go into trialogue with the Council and the Commission. So that's one element that will help to achieve this zero-emission building stock. But we know also that exchanging information with many stakeholders is crucial. So each webinar will invite one or more experts to deep dive on one specific aspect that is relevant for this transition. And the aim is also to have enough time for questions with the audience during each webinar. For our first webinar, I'm very pleased to introduce Elisabeth ZEYEN from the Berlin Institute of Technology. She will speak about the role of buildings in a highly renewable energy system. Elisabeth is a PhD student in energy system modeling at the Technical University of Berlin in the group of Professor Braun. She has a background in physics and is also open source developer of Python for power system analysis. So that's an open source toolbox for simulating and optimizing modern power and energy system. Her PhD is focused on the pathways to reach a carbon neutral European energy system. And today, she will present her work using this modeling of the energy system on scenarios to reach net zero emission buildings. And our model co-optimize both the supply and the efficiency measures on buildings. And I think we can learn a lot from it. So Elisabeth, thank you for joining us today. The floor is yours.
Thanks a lot for the introduction. Let me share my screen. All right, thanks a lot for the introduction. I'm going to present to you today some work which was published about 1.5 years ago in Energy, and it's about how to mitigate space heat demand peaks in buildings in a highly renewable European energy system. This work was done together with Professor Hagemeyer and Professor Braun, who's my supervisor, and was conducted at KIT. So today, the heating sector accounts to about 40% of the total CO2 emission in Europe, and therefore it does play a key role in reducing overall costs and greenhouse gas emissions. And many scenarios to reach net zero, they basically rely on electrification on the building sector. So instead of, for example, using gas boilers, which are used today in most of the buildings, using heat pumps. But this electrification of the building sector comes with a challenge because both demand and supply depend on weather. We can see this challenge also in the right graphic here. So here's shown the European heat demand in 2020, and we can see the strong seasonality. So there's a high heating demand in winter months and a very low demand, basically, or most of it for hot water in the summer months. And this is quite challenging in a highly renewable energy system because we basically would need capacities to supply this electricity for the heating only seasonal in winter months and not for the rest of the year. So in this work, we basically wanted to look on those heat demand peaks First of all, we wanted to understand better how those heat demand peaks influence the costs and the design of a highly renewable European energy system. And second, we wanted to look at different instruments and find out which are most suitable to mitigate these heat demand peaks. In our model, we want to optimize both at the same time. So the costs for heat supply. So for example, electrifying the heating sector, replacing gas boilers by heat pumps, but also the costs for efficiency measures, so renovating the buildings. And we co-optimize both in one European model with a high temporal resolution. Let me quickly introduce you to the model used. It's called PIPESA EURSEC. It's an open source, open data model. So you can basically run it by yourself. It's available on GitHub. It's covering all of Europe with hourly resolution. For this study, we have conducted a network with 45 regions, which you can see on the left-hand side, with the current electricity transmission grid. It does include various sectors, so it includes land transport, heating for building, and also electricity, and the interconnection between those sectors. So for example, electricity can be converted to hydrogen via electrolyzers. We do have electric vehicles, but also electricity can be fed back to the grid by vehicle to grid. We do consider also storage for the various carriers, and we have different loads. If we are looking more closely to how the heating sector is modeled, we see on the right-hand side the different loads. So we basically separate district heating, which you can see on the top, and individual heating. And the individual heating is further subdivided into urban areas and rural areas, and those are subdivided again into the residential and the service sector. We do assume historical heat demand from the JRC IDEs and basically have typical daily patterns which depend on weekday or weekend and the sector, so the residential or the service sector. As energy carriers to supply the heat, we assume biomass, hydrogen, methane, and electricity. And then we have various technologies which basically can satisfy the heating demand. So for the district heating, we have CHPs, which can run with biomass or gas, fuel cells, central solar thermal collectors, gas boilers, heat pumps, resistive heaters. And for the individual heating, we co-optimize the gas and electricity distribution grid, and then heat can be supplied by heat pumps, again, air or ground heat pumps, resistive heaters, gas boilers, or solar thermal collectors. What we at the end do in the as the optimization problem is that we minimize the total system costs. So we sum up the operational costs and the annualized capital costs of all components, and we optimize the transmission, the storage, the generation, all at the same time. The total system is hourly resolved for one distinct year. And for this study, we assumed a system with net zero CO2 emissions. We looked at different instruments to mitigate space heat demand peaks. And the three instruments were thermal energy storage, backup gas boilers, and building renovation. And we wanted to analyze the individual effects of these three, but also the combined ones. The thermal energy storage we assumed in two different forms, one for short-term and another one for long-term storage. The gas boilers are used as a backup for heat pumps for hybrid heating. And building renovation was assumed by additional insulation material and replacing energy inefficient windows. We modeled building renovation on a large scale. So basically for a whole country, we had data for the country-specific building stock, which depended on age, insulation state, and also the different building types. So how many single-family houses do we have? How many apartment blocks? And we generated for every country and for every sector, so the residential or the service sector, some cost curves, which you can see in the plot here on the slide. So we wanted to know how much does it cost to basically reduce the space heating demand by a certain percentage in each country. So we determined these energy cost curves based on the space heating demand, considering the losses by transmission and ventilation, and the heat gains, for example, by internal heat gains, but also by solar heat gains. The costs for renovation measures were calculated based on additional insulation material, which is needed for floor, wall, and roof, and the replacement of energy inefficient windows. We didn't optimize basically the renovation of single components, so just renovating the roof or just renovating the wall, but we had basically some renovation measures where all of the, like a certain amount of the wall, roof and floor were renovated at the same time. And this is based on monitored renovations. You can see here as an example the cost renovation cost for Bulgaria in red, for Germany in green, and for Sweden in blue. And we assumed in the model two possible renovation steps, one moderate one and one more ambitious one. As I said before, we assumed three different balancing tools: the building renovation, the thermal energy storage, and the individual gas boilers. But we also wanted to look on the combined effects of these. So we had in total 8 different scenarios. The most flexible one on the top, where we had all of the 3 balancing tools, building renovation, thermal energy storage, and individual gas boilers available. Then a rigid one where we had none of them, and then the other 6 where we basically altered all possible combinations of those tools. If we are looking on the total system costs of those 8 scenarios, we can first see, so on the left-hand side, we have the most flexible scenario with all available mitigating tools. And on the right-hand side, the rigid scenario without any. And if we have all tools available, 17% of the total system costs can be saved. Most effective of all those 3 tools is building renovation. So if you look here on the 4 bars, on the first 4 bars, these all include building renovations, and just retrofitting the buildings leads to cost savings of up to 14%. If we do have building renovation in place, then basically we don't really need individual gas boilers anymore. So basically the gas distribution could be removed with only 1 to 2% higher total system costs. The second most impactful tool is the backup gas boilers. They can save up to 6% of the total system costs. And the lowest impact in terms of total system costs had the thermal energy storage, where up to 3% of the total system costs were saved. Using those tools to mitigate heat demand peaks is not only important in terms of total system costs, but it can also avoid public acceptance problems, because we do need less generation, for example, in form of wind farms, storage and transmission capacity, and also distribution capacity. Here we are looking at one example week for the thermal supply in southwest France. So what you can see column-wise are three different scenarios. So on the left-hand side is the rigid scenario, where we don't have any balancing tool available. In the middle one, we have individual backup gas boilers and thermal energy storage, but no building renovation. And in the right hand or in the right column, we have all three balancing instruments available. And row-wise, you can see the different heating sectors. So we have first the rural area, again split into service and residential. The urban area, which is individually heated, and the district heating area. The graphic is showing the balance of the thermal supply. So positive values are basically how the heat is satisfied, and negative values are at which point in times the thermal energy storage is charging. If we first look on the first left column, we can see that in rural areas and in urban areas which are individually heated, all the heat is supplied by heat pumps, while in the district heating area, the heat is supplied by hydrogen or biomass CHPs in this specific region for this 1 week in January. If we do have backup gas boilers and thermal energy storage available, as you can see in the second column, basically at points where we have peak demand, hybrid heating, the backup gas boilers start to supply some parts of the heating demand. So this is the orange area, which you can see here. And thermal energy storage is used and also charged at some points. It's used more in district heating area, because there it can also be used as a seasonal storage. If we have building renovation available, then there's a lot of building retrofitting for individual heated areas, while for district heating, we don't see in this area any building renovation at all. That's because basically in district heating areas, you have like multiple options how to supply the heat, and you have technologies on a large scale. So it's not really worth it to retrofit the buildings, and it's cheaper to supply the heat here. If we are looking on the country-specific results, we do see large differences for the different countries. So the cost-optimal solution has building renovation with space heat savings between 44 and 51%. But as you can see in the map, there are large differences between the countries. Those differences depend on basically the combination of two factors. On the one hand, the country-specific costs for the renovation, and they depend again on the status of the building stock, but they also depend on the costs for the energy supply during the heating season. So the generation mix within the country. For example, in England, the building stock is not in the best state compared to the rest of the European countries, but there are also really good wind potentials, which allow like a cheap energy supply in winter months, and therefore we don't see such a large building renovation. While in other countries, for example in Italy, we see very large heat savings, and that's also because like a large part of the generation mix is based on solar, where we have like a low feed in winter months. Also, when we are looking on the electricity prices per country, which you see in the upper right plot, there are large differences, especially, for example, for Belgium, between scenarios where we don't have any tool to mitigate the space heat demand peaks and all instruments available. Those electricity prices are basically an endogenous result of our optimization. So we don't give any fixed exogenous prices, but they are an outcome. We can also see that the prices are very seasonal, and that's because of the electrification of the heating demand. So we have some very strong peaks and with very high prices in the winter months. And they are reduced by up to 50% if we have some balancing instruments available. As mentioned in the introduction, I studied physics and we like thought experiments. So we have done one thought experiment to better understand what is the impact of those heat demand peaks. This is really just a thought experiment and shouldn't basically show any realistic behavior. But instead of having the varying heating demand, we have done 2 additional scenarios where we assumed that the heat demand is flat throughout the year. And we wanted to understand how much are our mitigating tools used in this case. And that's basically shown on the left plot here. So the first 4 rows are the scenarios with time varying heat demand. That's what we assumed and the results I've just been showing before. And the last 2 are our thought experiment where we basically assumed a flat heating demand throughout the whole year. If we assume a flat heating demand throughout the year, we nearly see no building renovation, and this basically emphasizes that building renovation is really needed to mitigate those heat demand peaks and not to reduce the overall energy consumption. If we look at the total annual system costs, that's what you can see in the right plot here, then we see that 30% of the total system costs are just caused by those heat demand peaks. And this again shows the importance on how to mitigate and how to handle those challenging points in time for the energy system. We have done multiple further sensitivities, which you can all find in the paper or in the supplementary material. So basically, we varied the costs for the electricity and gas distribution. We considered a larger electricity grid expansion. We looked at different weather years, the costs for renovation. We changed the district heating share, the efficiencies of the heat pumps, and we restricted the wind potentials. So if you have any further questions about that, feel free to ask them after the presentation, or also check out the paper and the supplementary material. I just want to quickly show you the results of 3 of those sensitivity scenarios. One is the increase in district heating share. So basically in the main scenarios, we assumed that the district heating share would stay constant as what it is today, but there are many plans to basically increase the district heating share. And that's what we've done in one of the scenarios. If we do so, building renovation is still an important measure to deal with the heat demand peaks, and also thermal energy storage is getting more important because it can be used as a seasonal storage for district heating. And basically those backup gas boilers are getting less and less important. That's just because for district heating, you have the option of multiple different technologies which can supply heat. We also varied the costs for the retrofitting, actually out of two reasons. There's like a high uncertainty about what the costs for building renovation are going to be in the future. But also there's a high uncertainty in the building stock data which we used. And one can see that there's a strong dependency on the total system costs, depending on how much the costs for building renovation are. But even with 40% higher costs, we still see a large usage of the building renovation. We also looked at different weather years. So we took weather data from 6 different years. And what we find what is most important for the usage of those mitigating tools is not the average temperature within the year, but really the coincidence of having very cold days and at the same time low wind capacities. So the most expensive year and the one with the highest building renovation was 2010, because there we had multiple days in winter which were very cold with very low wind at the same time. Coming to the conclusion, up to 30% of the total system costs are caused by seasonal heat demand peaks. From the 3 tools which we looked at, thermal energy storage, backup gas boilers, and building renovation had the largest lever to reduce total system costs by up to 14%. If we have efficiency improvements, all gas distributions to buildings can be excluded with only 1 to 2% higher total system costs. And the investments in energy efficiency in buildings are really driven by the need to reduce the peak demand and not the overall energy consumption. Since I was referring the whole time to the paper already, you can check it out under this DOI, and I can also put a link into the chat, and it's open access. Thanks a lot.